Okay, I'm back here to do some more problems from this section on trig integrals and trig substitution. So let's see here, where did I leave off? What did I do last? I forgot what I did last. I think I did number 13. Yeah, I did 13. So let's look at 14. 14, integral, let's see, cotangent to the fifth theta, sine to the fourth theta, d theta. All right, so again on this one, it's kind of like the previous problem that we did. We don't have sine and cosine explicitly here. So what I'm going to need to do is first rewrite this cotangent. So I'll go ahead and rewrite the cotangent as, cotangent, remember, is the reciprocal of tangent. Tangent is sine over cosine. So this is going to be cosine to the fifth theta over sine to the fifth theta. And then I have sine to the fourth theta d theta. And I get 4 of my factors of sine to cancel out, which leaves me 1 factor of sine here, which leaves me integral cosine to the fifth theta over sine theta d theta. And just like the previous problem, I'm trying to find which of these to choose as my u. I don't want to choose cosine as my u because du is in the denominator. That's hard to deal with. But if I choose my u to be sine theta, the derivative is up here, and I can split one of these cosines off to make the derivative appear over here. So I'm going to rewrite the integral first and peel off 1 factor of cosine. And now you can see here I've got u and there's du. So my substitution here is u is sine theta, du is cosine theta, d theta. I have that exactly right here. So I'm going to replace that with u, that with du, and now I need to get this taken care of, the cosine of the fourth. And I can use this substitution here. I need to get this in terms of sine. So all we do now is just rewrite cosine using the Pythagorean identity. Since I have cosine to the fourth, an even power of cosine, that's a good thing, because I can write it as cosine squared. So this will be equal to integral cosine squared theta squared over sine theta and then cosine theta d theta. And remember that cosine squared theta is 1 minus sine squared theta. So you have 1 minus sine squared theta squared over sine theta cosine theta d theta. So we're making good progress here. Now I've got all the stuff over here has sine in it, which means I can replace them with u's, and cosine theta d theta is my du. So now rewriting this integral, I have 1 minus u squared squared over u and then du. And at this point what I can do is expand out the numerator. This will become 1 minus 2u squared plus u to the fourth on top over u. I really don't need the parentheses here. Okay, and then du, like that. And now I have 1 term in the denominator, 3 terms in the numerator. I can split this up into 3 separate fractions and use the power rule on 2 of them, and on 1 of them it's going to be a natural log when I take the antiderivative. So this becomes integral, okay, first one, 1 over u, and then minus 2, and then u squared over u is just u, and then plus u to the fourth over u is u cubed. du. And now I just take the antiderivative of each of these. So antiderivative of 1 over u is natural log absolute value of u minus, okay, antiderivative of u is 1/2 u squared, but then I had a 2 here. The 2 and the 1/2 just go away, so I get u squared. And then the antiderivative here is 1/4 u to the 4th, then plus my constant. And now I'm going to come in here and replace all my u's with sine theta. So natural log sine theta, and then minus sine theta, but I'm squaring it, plus 1/4 sine theta, but I'm raising it to the 4th, and then plus c. And that should do it. All right, let's move on to number 15. All right, so 15, 1 minus sine x over cosine x. Over cosine x dx. Well, initially, I see I can split it in 2 fractions because I have 1 over cosine, sine over cosine. Let me just write that down. That would be 1 over cosine x minus sine x over cosine x dx. 1 over cosine is secant x minus sine over cosine, which is tangent x dx. And then remembering that our formula sheet does actually have the antiderivatives for all of the trig functions that are just by themselves. So like the antiderivative of secant is number 14 on the formula sheet, and antiderivative of tangent is number 12. So I can go straight to a formula here. These are all equal. This is equal to, okay, the antiderivative of secant is going to be natural log absolute value secant x plus tangent x, and then minus the antiderivative of tangent x, which is natural log of secant x. Now there are other ways you can do this problem, but I think that's probably the easiest way. So I'll stick with the easy way. All right, let's look at number 16. I like them when they're nice and easy like that. Just remember, if you have an integral with sine, cosine, tangent, secant, cosecant, or cotangent, all of those have formulas. So if we get them where they're just by themselves, we're happy campers. All right, cosine squared x, sine 2x. All right, so remember this is sine 2x like this, like in parentheses. All right, so we can't work with those together right now because the argument here is x, the argument here is 2x. We either need them to both be x's or both 2x's. So I'm going to go and just use my double angle identity from pre-cal and rewrite sine 2x as 2 times sine x times cosine x dx. I'm going to pull the 2 out of the integral and put the cosine and cosine together, get cosine cubed x times sine x dx. And this one is pretty straightforward because we got sines and cosines together. They're actually both to an odd power. I'm going to go ahead and choose my u to be cosine because that'll become u cubed, and then this is the derivative of cosine. I'm off by a sign. So u is going to be cosine x, du is negative sine x dx Move that negative over. And then I'll just rewrite the problem. This is equal to, I had a 2 out here. Cosine x is u, so u cubed. And then sine x dx is negative du. Here's my du, here's my negative. So it's going to change it to a negative 2. And it doesn't get much easier than that. The antiderivative there, I have a negative 2 out front. Antiderivative of u cubed is 1/4 u to the 4th plus a constant. And remember, u is cosine. So put these together, negative 1/2 cosine to the 4th x plus c. That's it. This is your answer right here. (17) It's a long homework assignment. All right, tangent x, secant cubed x. Tangent x, secant cubed x dx. Now, this is where we're moving into a different sort of strategy, because if we know if we have sines and cosines, we'll do certain things. But if we see secants and tangents, we do something else. So in your notes, I believe I gave you something on the strategy for this. Let me see. So if the power of secant is even, we're going to do a certain thing. Here the power of secant's not even. If the power of tangent is odd, which it is because it's 1, then we do something else. And this is what we do. Tangent power is odd. We save a factor of secant tangent and use a Pythagorean identity. Our u substitution is u is secant x. So let me just write down the substitution first. That's going to be our substitution. And let's see why that substitution is going to work. The derivative of secant x is secant x tangent x dx. And so what I'm looking for is to try and get a secant x tangent x out of this. So notice that if I take the tangent x out over here and peel one secant off of that, I get secant squared x times secant x tangent x. So I'm just rewriting the integral, right? This is still secant cubed, and then here's tangent. But notice that secant x tangent x dx is du right here. So that means that I've got to come in here with what's left and somehow get that in terms of secant, which it already is. So this is going to be straight away, u is going to be secant x, so u squared. Then everything out there is du. The antiderivative here is 1/3 u cubed plus c, which is 1/3 secant cubed x plus c. So that's it. Let's take a look at the next one. Tangent squared secant to the 4th. Number 18. Tangent squared secant to the 4th. So with this one, my tangent is not odd. My secant, however, is even. So when we have an even secant, the strategy is to peel off a secant squared. So I'm gonna peel off a secant squared, and I'm gonna let u be tangent x. So u is tangent x. The derivative of tangent x is secant squared x dx. So remember, the idea was peel off a secant squared, because if this is even, you're definitely going to have a secant squared. So this will become integral tangent squared x times secant squared x times secant squared x dx. That's multiplication. So I've peeled off a secant squared x dx, and that's because this matches up here. So I've got du right there. I can replace my tangent with u, so this will become u squared. But what about the secant squared? I don't call it du again because this is du. I would need the dx there with it. So I need to somehow rewrite this in terms of tangent. So you got to go back and remember some Pythagorean identities. 1 plus tangent squared x equals secant squared x. That's Pythagorean identity. And so if I want to know what secant squared x is, here it is. And that's in terms of tangent. So what I'll do is I'll come over here, I'll leave tangent squared x alone out here. I'll replace secant squared x with 1 plus tangent squared x. Have to have it in parentheses because it's two terms, and that tangent would distribute if we multiplied that. Secant squared x dx. So there's my du. Here's u squared. Here's 1 plus u squared. So I can go directly to my substitution now. U squared, 1 plus u squared du. Then distribute my u squared through. U squared plus u to the 4th du. And then power rule. 1/3 u cubed plus 1/5 u to the 5th plus c. And then replace our u's with tangent x. So 1/3 tangent x but cubed plus 1/5 tangent x to the 5th plus c, and that's our answer. So showing you two different strategies when you have tangent and secants together. All right, let's look at 19. Tangent squared x dx. So if that was just tangent, you would just go to your formula, because we have formula when the trig function's by itself. Of course, you can't put it tangent, tangent, and then do each one, because that would be like breaking the rules of products. You can't integrate products by just integrating them separately. So I don't know what the antiderivative of tangent squared is. That's what we're trying to figure out. But I do know this, going back to this identity, the Pythagorean identity, 1 plus tangent squared x equals secant squared x, that if I move the 1 over, just subtracting it on both sides, that I can rewrite it this way. Now, what's the advantage of that? Well, the advantage is that with these two terms, I actually do know the antiderivative of secant squared, because in Cal 1, I learned that the derivative of tangent was secant squared x. So the antiderivative from this should just go back up to tangent. And then, of course, the antiderivative of 1 with respect to x is just x. So integrating both of those separately, you get that. And that's it. We're done. Let's check it real quick. We haven't checked many of these. What's the derivative of this? Secant squared x. What's the derivative of that? Minus 1. And what's secant squared x minus 1? It's tangent squared x. So it works. 20. Tangent squared x plus tangent to the 4th x. Tangent squared x plus tangent to the 4th x dx. Well, I could split this up into two. I could split this up into two because I have two terms, and I know the antiderivative of tangent squared x. I just did that problem. But tangent to the 4th is a little different because I can't use the Pythagorean identity with that one the way I did the other one. The reason being that I can replace tangent squared x with secant squared x minus 1. I can do that, but if this was to the 4th power, then this would be the same as squaring this, and that would mean square that, and then you'd have to expand that out, and that does not look fun. But let me just try some things here. Let me factor out a greatest common factor. Tangent squared x is a common factor. Get 1 plus tangent squared x here. So if I distribute this, I get that. But wait a minute. Tangent squared x plus 1 is secant squared x. Maybe this will help. Tangent squared x times secant squared x dx. So just replacing this with secant squared x. And now I have a tangent and secant appearing together. I've got an even power on secant. Whenever that happens, I let u be tangent x. The derivative of that is secant squared x dx. I have secant squared x dx. I just need to make sure I rewrite this. But u is tangent. So this is just going to be integral u squared du. That's it. And then the antiderivative there is 1/3 u cubed plus c, which will be 1/3 tangent x cubed plus c. That's it. We're good to go. Kind of weird that it works that way, but it does. All right, let's look at 21. Tangent to the fourth, secant to the sixth. This does not look fun. Tangent to the fourth, x, theta, what is it, x? Secant to the sixth x dx. So you have tangents and secants appearing together. Your secant is to an even power, and because of that, you're going to peel off a secant squared. U will be equal to tangent x. Du will be equal to secant squared x dx. Let me try this. Integral tangent to the fourth x. Let's see, I'm peeling off a secant squared x, which leaves me with a secant to the fourth x. That's du right there. My tangent can be replaced with u, so that's u to the fourth. So what about secant to the fourth? I've got to figure out what that is. Now hold on, I'm getting a text. Let me just check out what this is. Let me find him. Where is he?
I'm
Hey,
sorry.
come on.
He was in there recording a lecture. I know where to find you.
Yeah, I was trying to get something done. How's it going?
Good, how are you, sir?
Come in real quick.
Sorry to interrupt.
No, it's okay. Let me finish this problem out. Just have a seat. All right. Okay, so we've got to deal with the secant to the fourth. So going back again, we had said by the Pythagorean identity, secant squared x is 1 plus tangent squared x. And so if this is to the fourth, we can say that that's that squared, and then that means it's that squared. So what I'll do is I'll replace secant to the fourth x, which is this, with that. So we've got integral tangent to the fourth x, and then in parentheses, 1 plus tangent squared x, but then that quantity squared, and then secant squared x dx. And now I make my substitution, u is tangent. So when I make the substitution, I've got integral u to the fourth, 1 plus u squared squared, and then that's du. And that one right there, we should be able to handle because it's polynomial. So we're just going to go now and let's expand this out. So integral u to the fourth, and then we get 1 plus 2u squared plus u to the fourth. And then we distribute this through. So u to the fourth plus 2u to the sixth plus u to the eighth. And now we're there. Power rule. 1/5 u to the fifth. Let's see, plus 2/7 u to the seventh plus 1/9 u to the 9th plus a constant. And now final step is replace all your u's with tangent x. So we have 1/5 tangent x to the 5th plus 2/7 tangent x to the 7th plus 1/9 tangent x to the 9th plus a constant. That's it. That was it. All right, let me pause it.